All right, welcome back to another video. So, last video, we're reading the book Mathematics for Machine Engineering. Now, this is a bit of a strange choice, right? Because there's a lot of different things I could do on my channel. So if we go to my playlists and just take a look at some of them, we've got a lot of unfinished playlists here. We've got NVIDIA certification. We've got prompt engineering. That would be a really good one. We've got reading the AI data center Juniper validated design. That would be a solid one as well. CCNP data center. So there's a lot of unfinished things. I also promised a home office setup video for working outside that hasn't been delivered yet. So lots of things started and not stopped. So why switch? Why do the mathematics instead? Cosmic Python's another one where I didn't read the book all the way through. And you know what? That's actually a good question. I'm kind of not sure. I feel like yeah, the NVIDIA certification and the AI data center validated design. Basically, any certification would probably be better than this. But I think an answer is if we look at the long term. So I'm 39. I'm about to be 40. So my 5-year plan, I think, because things have been pretty tumultuous for the last few years, and I went from when I was how old, like 28, so pretty late in my life, I decided to further my education. I was a viola player, and I wanted to play for a major city orchestra. That was the plan. Some like probably pay like 50K, something like that per year, and then I'd live in like Chicago or something, and then I would play in the orchestra. Or it could be like any city, Austin, Madison, Milwaukee, something like that. I would play in the orchestra and I would teach, and that was my plan. Didn't work out. Whether you can believe it or not, it didn't work out. So I had to make a new plan, and I was just kind of lost in limbo for many years. I was in and out of school. I was out of higher ed, out of community college. I was having a lot of mental health struggles as well, and the years went by, and I was lucky to work a job for like $10 an hour. So what I decided to do was really get serious about furthering my education and changing my career to be a computer professional. And I decided to do this because I met other computer professionals and I just realized, oh, these are my people. This is where I belong. So, it was a little bit arbitrary in a sense. I picked networking rather than security. Security might have been a better choice. I also stayed with networking rather than pivoting to cloud, which was probably not the best move. But here I am now looking towards the future. And what do I see in the future? AI. As I've mentioned, I've read Situational Awareness by Leopold Aschenbrenner. We have ChatGPT, which, as impressive as it is, it's probably, according to the trend lines, it should grow by 2 orders of magnitude. If we look in the past, 5 years in the past, we did not have ChatGPT at all. It was 2019, and I don't even think we had the underlying technology in its current form, GPT-3. I think in 2019 we might have only had GPT-2, but this is what's crazy about the modern world. We can ask that to the AI. In 2019, did there exist GPT-3 or was there only GPT-2? So there you have it. Only GPT-2 existed publicly. GPT-3 was developed and trained, but it wasn't released until the next year in 2022. So GPT-2 was the largest publicly available model from OpenAI in 2019. So that was 5 years ago. So what's going to happen if you look 5 years in the future? Right now, so tell me which model right now in the year 2024 is being trained that is likely to be released in the next few years. Yeah, so several models are under development with anticipated releases. GPT-5, Gemini 1.5, Llama 4. So this isn't slowing down. We are in the middle of a revolution, an AI revolution that is going to completely unrecognizably change the world. Everyone will have a PhD professor in any subject they can imagine with a 300 IQ, willing and ready to answer any questions they have. Right now we have that at somebody who's like a smart high schooler, college level student, and it's just going to get smarter and smarter and smarter from here. And there'll be a point where it gets so smart that it will scare governments all around the world, and there will be a crackdown of security. And security, bluntly, and not, security will be a big part of AI going forward. So we're gonna have a lot of changes. So if I were to look ahead to the next 5 years, I'd be foolish to ignore AI. In my opinion, AI is gonna be the most important thing there. But what about next year? I'd be foolish not to renew my CCNA, right? I'd be foolish not to renew my to get again my CCNP. I'd be foolish, to lose the short term for the long term, right? Well, not necessarily, because as I mentioned before, we have WGU, Western Governors University, which has accreditation. So it has every program. Accreditation doesn't work program by program, college by college in a university. It works university as a whole. So if I get a bachelor's degree, and I already have a network engineering and security degree, or I already have a degree in that. I have an associate's degree. So, right there, security is going to be huge. So if I get a degree in this, that knocks off the prereq for the UT program for AI, and I'm not sure which school it's a part of. I think it's a part of the maybe engineering. Yeah, so here it is. So let's see if yeah, I'm not so sure what this what it's a part of, but I could get a master's in artificial intelligence within 5 years, and now I'm a security expert, and I have a master's in AI. Like how does that sound? It sounds good to me. So, that's a lot of work, right? I have to, right now, my math, I'd be lucky if it was at a high school level. My even like my English reading and writing is probably not that advanced. I did take English courses and have to do stuff like that for my 2-year degree. But, you know, depending on what the elective courses are, if it's like English 3 and I have to read like 50 books in a day, you know, I might have trouble doing that, right? So it's going to be a lot of work. It's going to be a lot of math, but it's a clear pathway to success in my opinion. So and it's the same thing I did back when I was lucky to make $10 an hour as a failed musician. You know, it's like I went to school, furthered my education, and worked with the skills and education I got in doing so. So that's my 5-year plan. I want to go back to school and further my education. I want to go from having an associate's degree to having a bachelor's degree. And then I want to go from having a bachelor's degree to having a master's degree in artificial intelligence. So now I have a master's in networking, which I already have a near 10-year professional experience in. And then a bachelor's degree that includes that, but also is all about security as well. So now I'm a security guy in the age of security crackdowns on AI. And by the way, I also have a master's in artificial intelligence. So would you hire me? I whoever you are, I would. But you know that's the 5-year plan. So here and now today, I think pre-exposure to the hard stuff will help. So if I could even get the textbooks or whatever that they expect of me now and start working on them now, you know, I'd have a head start. I'm going to be pressed for time. So if that's my goal, to get a master's degree in artificial intelligence, you know, what else would make more sense than to read the mathematics for machine learning? So speaking of that, let's get started. All right, and then the last video, we read all about the symbols, and then we also made some tools here to help learn about them. So we've got the table of abbreviations and acronyms. We've got statistical, probabilistic, and optimization related symbols, and all the other symbols in the table of symbols. So it'll be really easy to skip back to that table by just going to all items, highlights, and yellow, and then we can very easily skip back if there's some unrecognized symbol. All right, so with that, let's try to make some progress on this book. So the first chapter is Introduction and Motivation. And I'll do a sound check now. And, okay, okay, I am getting sound, okay, okay, good. So machine learning is about designing algorithms that automatically extract valuable information from data. The emphasis here is on automatic. And IE is under, in other words, right? Or is it EG? See, this is why we have this. So IE means this means, EG means for example. Okay, so the emphasis is on automatic. For example, machine learning is concerned about general purpose methodologies that can be applied to many data sets while producing something that is meaningful. There are 3 concepts that are at the core of machine learning: data, a model, and learning. Since machine learning is inherently data-driven, data is at the core of machine learning. The goal of machine learning is to design general-purpose methodologies to extract valuable patterns from data, ideally without much domain-specific expertise. For example, a large corpus of documents, and EG does mean for example, rather than and again, I can refer to this. Yep, rather than this means. For example, rather than this means. For example, given a large corpus of documents, for example, books in many libraries, machine learning methods can be used to automatically find relevant topics that are shared across documents. Hoffman et al., 2010. To achieve this goal, we design models that are typically related to the process that generates data, similar to the data set we are given. For example, in a regression setting, the model would describe a function that maps inputs to real-valued outputs. To paraphrase Mitchell, 1997, a model is said to learn from data if its performance on a given task improves after the data is taken into account. The goal is to find good models that generalize well to yet unseen data, which we may care about in the future. Learning can be understood as a way to automatically find patterns and structure in data by optimizing the parameters of the model. So, data model learning. While machine learning has seen many success stories and software is readily available to design and train rich and flexible machine learning systems, we believe that the mathematical foundations of machine learning are important in order to understand fundamental principles upon which more complicated machine learning systems are built. Understanding these principles can facilitate creating new machine learning solutions, understanding and debugging existing approaches, and learning about the inherent assumptions and limitations of the methodologies we are working with. All right, so chapter 1.1, finding words for intuitions. A challenge we face regularly in machine learning is that concepts and words are slippery, and a particular component of the machine learning system can be abstracted to different mathematical concepts. For example, the word algorithm is used in at least two different senses in the context of machine learning. In the first sense, we use the phrase machine learning algorithm to mean a system that makes predictions based on input data. We refer to these algorithms as predictors. In the second sense, we use the exact same phrase, machine learning algorithm, to mean a system that adapts some internal parameters of the predictor so that it performs well on future unseen input data. Here we refer to this adaptation as training a system. This book will not resolve the level of ambiguity, but we want to highlight upfront that, depending on the context, the same expressions can mean different things. However, we attempt to make the context sufficiently clear to reduce the level of ambiguity. The first part of this book introduces the mathematical concepts and foundations needed to talk about the three main components of a machine learning system: data, models, and learning. We will briefly outline these components here, and we will revisit them again in Chapter 8 once we have discussed the necessary mathematical concepts. So that was about training. The next one is about data as vectors. While not all data is numerical, it is often useful to consider data in a number format. In this book, we assume that data has already been appropriately converted into a numerical representation suitable for reading into a computer program. Therefore, we think of data as vectors. As another illustration of how subtle words are, there are at least three different ways to think about vectors: a vector as an array of numbers, a computer science view; a vector as an arrow with a direction and magnitude, a physics way; and a vector as an object that obeys addition and scaling, a mathematical view. And that's why a lot of this stuff is hard to understand, because the same words are used in different contexts. Next section is about a model. A model is typically used to describe a process for generating data, similar to the data set at hand. Therefore, good models can also be thought as simplified version of the real unknown data generating process, capturing aspects that are relevant for modeling the data and extracting hidden patterns from it. A good model can then be used to predict what would happen in the real world without performing real world experiments. And I actually do want to highlight this because I think it is important to illustrate how subtle words are in a mathematical context. It's really, you can't be lazy with your words. You have to be very clear about exactly what word you're intending to use in exactly which context. So if we highlight it in blue rather than yellow, now we get our own highlight and we can preserve the table there. So there we go, blue. And then bookmarks are also not cluttered. All right, so the next part is learning. We now come to the crux of the matter, the learning component of machine learning. Assume we are given a data set and a suitable model. Training the model means we use the data available to optimize some parameters of the model with respect to a utility function that evaluates how well the model predicts the training data. Most training methods can be thought of as an approach analogous to climbing a hill to reach its peak. In this analogy, the peak of the hill corresponds to a maximum of some desired performance measure. However, in practice, we are interested in the model to perform well on unseen data. Performing well on data that we have already seen, training data, may only mean that we found a good way to memorize the data, and that's overfitting. However, this may not generalize well to unseen data, and in practical applications, we often need to expose our machine learning system to situations that it has not encountered before. Let us summarize the main concepts of machine learning that we cover in this book. We represent data as vectors, and we represent data as vectors in the computer science sense. So let's go back and read what a vector means in the context of this. In the context of the computer science view, a vector is an array of numbers. All right, so the next summary of the main concepts of machine learning that are covered in this book is we choose an appropriate model, either using the probabilistic or optimization view. And then the last one is we learn from available data by using numerical optimization methods with the aim that the model performs well on data not used for training. All right, let me check the clock. Looks good. Okay. So, chapter 1, section 2. 2 ways to read this book. We can consider 2 strategies for understanding the mathematics for machine learning. Bottom up, building up the concepts from foundational to more advanced. This is often the preferred approach in more technical fields such as mathematics. This strategy has the advantage that the reader at all times is able to rely on their previously learned concepts. Unfortunately, for a practitioner, many of the foundational concepts are not particularly interesting by themselves, and the lack of motivation means that most foundational definitions are quickly forgotten. Next approach is top-down, drilling down from practical needs to more basic requirements. This goal-driven approach has the advantage that the readers know at all times why they need to work on a particular concept, and there is a clear path of required knowledge. The downside of this strategy is that the knowledge is built on potentially shaky foundations, and the readers have to remember a set of words that they do not have any way of understanding. We decided to write this book in a modular way to separate foundational mathematical concepts from applications so that this book can be read in both ways. This book is split into two parts, where part 1 lays the mathematical foundations and part 2 applies the concepts from part 1 to a set of fundamental machine learning problems, which form 4 pillars of machine learning as illustrated in figure 1.1: regression, dimensionality reduction, density estimation, and classification. Chapters in part 2 mostly build upon the previous ones, but it is possible to skip a chapter and work backward if necessary. Chapters in part 2 are only loosely coupled and can be read in any order. There are many pointers forward and backward between the two parts of the book to link mathematical concepts with machine learning algorithms. Of course, there are more than 2 ways to read this book. Most readers learn using a combination of top-down and bottom-up approaches, sometimes building up basic mathematical skills before attempting more complex concepts, but also choosing topics based on applications of machine learning. So we have figure 1.1, the foundations and 4 pillars of machine learning. So you got to learn about regression, you got to learn about dimensionality reduction, you got to learn about density estimation, and then you've got to learn about classification. So therefore, you need to learn vector calculus, you need to learn probability and distributions, you need to learn linear algebra, you need to learn analytic geometry, and then you also need to learn optimization and matrix decomposition. So let's highlight that so we can go back and see what we need to learn. So, of course, there are more than 2 ways to read this book. Most readers learn using a combination of top-down and bottom-up approaches, sometimes building up basic mathematical skills before attempting more complex concepts, but also choosing topics based on applications of machine learning. Part 1 is about mathematics. The 4 pillars of machine learning we cover in this book, see figure 1.1, which we have bookmarked in blue, require a solid mathematical foundation, which is laid out in part 1. We represent numerical data as vectors and represent a table of such data as a matrix. The study of vectors and matrices is called linear algebra, which we introduce in chapter 2. The collection of vectors as a matrix is also described here. Given 2 vectors representing 2 objects in the real world, we want to make statements about their similarity. The idea is that vectors that are similar should be predicted to have similar outputs by our machine learning algorithm, our predictor. To formalize the idea of similarity between vectors, we need to introduce operations that take 2 vectors as input and return a numerical value representing their similarity. The construction of similarity and distances is central to analytic geometry and is discussed in chapter 3. So you need linear algebra and analytic geometry. In chapter 4, we introduce some fundamental concepts about matrices and matrix decomposition. Some operations on matrices are extremely useful in machine learning, and they allow for an intuitive interpretation of the data and more efficient learning. We often consider data to be noisy observations of some truly underlying signal. We hope that by applying machine learning, we can identify the signal from the noise. This requires us to have a language for quantifying what noise means. We often would also like to have predictors that allow us to express some sort of uncertainty. And e.g. means, for example, to quantify the confidence we have about the value of the prediction at a particular test data point. Quantification of uncertainty is the realm of probability theory and is covered in Chapter 6. To train machine learning models, we typically find parameters that optimize some performance measure. Many optimization techniques require the concept of a gradient, which tells us the direction in which to search for a solution. Chapter 5 is about vector calculus and details the concepts of gradients, which we subsequently use in Chapter 7, where we talk about optimization to find minima / maxima of functions. So we also need optimization, vector calculus, we need probability theory, we need matrix decomposition, analytic geometry, and linear algebra. So let's see if we got that on Khan Academy, because I'm a big fan of Khan Academy. I love the concept. I wish they'd have a Khan Academy more for adults. But I like the concept. I think it's important that they have it for kids. Let's see. So they definitely have AP Calculus on there. Let's see if there's anything on here that looks familiar. There we go. Linear algebra. Perfect. And then so linear algebra is needed. Probability theory and vector calculus as well. So let's see if they've got probability theory. So they've got AP statistics and AP calculus, which is probably useful. Yeah, AP college statistics, yeah, calculus, BC, yeah. So that's probably pretty useful. But here's the one I was looking for: statistics and probability. That's probably useful as well. All right, so part 2 is about machine learning. The second part of the book introduces 4 pillars of machine learning as shown in figure 1.1. We illustrate how the mathematical concepts introduced in the first part of the book are the foundation for each pillar. Broadly speaking, chapters are ordered by difficulty in ascending order. In chapter 8, we restate the 3 components of machine learning: data, models, and parameter estimation in a mathematical fashion. In addition, we provide some guidelines for building experimental setups that guard against overly optimistic evaluations of machine learning systems. Recall that the goal is to build a predictor that performs well on unseen data. So let's just search for a linear regression in Khan Academy. So we've got a worked example of linear regression using transform data. So this is part of AP College Statistics. So yeah, let's try to bookmark this. So okay, so we've already got that here. I've already worked on a lot of it too. All right. In chapter 9, we will have a close look at linear regression, where our objective is to find functions that map inputs there in that equation, and we'll dive into that deeper later on. We do have we can briefly look back and see what that was. So we got the bookmark advanced, so that's the yellow. So in the table of symbols, so here we go. So we'll have a look at linear regression, where our objective is to find functions that map these sorts of inputs. So we can see it's probably this one. So let's see if anything looks familiar there. Nothing there. Nothing there. And nothing there either. So oh, here we go. So here we've got the symbol. This is what gets frustrating. Oh, here we go. So A is an element. So yeah, it was in. Yeah, it was in this section. I just didn't see it. So A is an element of set A there. Yeah, so X is an element of this sort of set. IR comma raised to the power of this D looking symbol. And they're not necessarily I's, they're not necessarily R's, not necessarily D's. It could be part of the Greek alphabet. So we can look at that as well. Is this special IR character part of the Greek alphabet? Let's look at that. No, don't see it there. Okay, so the key objective, yeah. So the corresponding objects served values. Y is a set of that, which we can interpret as the labels of their respective inputs. We will discuss classical model fitting, parameter estimation via maximum likelihood and maximum a posteriori estimation, as well as Bayesian linear regression, where we integrate the parameters instead of optimizing them. Chapter 10 focuses on dimensionality reduction, the second pillar in figure 1.1, using principal component analysis. The key objective of dimensionality reduction is to find a compact, lower dimensional representation of high dimensional data, X being a subset of that, which is often easier to analyze than the original data. Unlike regression, dimensionality reduction is only concerned about modeling the data. There are no labels associated with a data point X. And let's unpack this into plain English. Let's ask the AI to do that. Okay, so yep, it should be able to see that plenty well. So the vector X is an element of d-dimensional space where each component of X is a real number. In other words, X is a vector with d real numbered entries. So for me to really, I think the best way for me to consider myself to have learned this is to be able to do exactly this, to be able to unpack this. Okay, so as I'm reading this book, which is titled Mathematics for Machine Learning, and I think mathematics in general, I think probably the best way for me to kind of consider myself to have really mastered the subject is to be able to unpack these equations and state them in the clear language. Well, not clear, but the language that you did, where you said, so the expression means the vector X is an element of, like if I can do that, and instead of just saying like, if I can unpack the symbols and the representations into plain English, I feel like that's a good strategy. Do you agree? Yeah. Exactly. All right. So, yeah, which is often easier to analyze than the original data. Unlike regression, dimensionality reduction is only concerned about modeling the data. There are no labels associated with a data point X. In chapter 11, we will move to our third pillar, density estimation. The objective of density estimation is to find a probability distribution that describes a given data set. We will focus on Gaussian mixture models for this purpose, and we will discuss an iterative scheme to find the parameters of this model. As in dimensionality reduction, there are no labels associated with the data points. The vector x is an element of d-dimensional space. Okay, well that didn't work. Well, let me try this. With data points, and then we'll get this unpacked by ChatGPT. However, we did not seek a low-dimensional representation of the data. Instead, we are interested in a density model that describes the data. Okay, so we're going to say rewrite this paragraph with the, so we're going to say rewrite this paragraph with the equation, with the mathematical statement unpacked, because it's not necessarily an equation, unpacked into plain English. Okay, so now let's reread this. So in chapter 11, we will explore our third main topic, density estimation. The goal of density estimation is to identify a probability distribution that effectively describes the structure and characteristics of a given data set. Our approach will focus on Gaussian mixture models. So it reframed quite a bit the language, but I think that's okay. A technique that combines multiple Gaussian or normal distributions to model complex data patterns. We will discuss an iterative process to determine the parameters that define this model. And let's look up a Gaussian distribution. And I don't know how to spell it, which shows how much I know about it. Okay, well, this is probably good enough. So it's a function of the base form with parametric extension. But, you know, that's the AI, so I don't know if it's right. Oops, I have to hit space and enter. All right, well, anyway, moving on. Chapter 12 concludes the book with an in-depth... Oh, you know what? I forgot to read the rest of ChatGPT's unpacking. Similar to dimensionality reduction, there are no predefined categories or labels for each data point in this dataset. Each data point is a vector, a list of numerical values that exists in a d-dimensional space, where d represents the number of features or measurements for each point. However, unlike dimensionality reduction, which seeks to condense the data into a smaller number of dimensions, our objective here is different. We aim to develop a model that captures the underlying density or distribution pattern of the entire dataset rather than reducing its dimensions. This density model will give us a better understanding of how the data is distributed across the d-dimensional space. Okay, and now use an analogy to make this like really intuitive for anyone living in the United States. All right, so imagine you're analyzing neighborhoods in a large US city to understand where people live without knowing any specific information about each resident's identity or job. Your goal is to create a map showing where people are likely to live based on general characteristics like income, level, family size, or property type. Each person in the city is represented by a data point with various details like age, income, number of children, and we place these details in a space where each type of characteristic has its own dimension. So if we're considering 5 characteristics, our space would be 5-dimensional. In real life, we don't think in 5 dimensions, but conceptually it just means we're using a unique axis for each characteristic to locate people in a complex map. So this is the one thing, is like if you listen to a lot of like Neil deGrasse Tyson, will be like, oh, you know, dimensions, math is the language of the universe. Oftentimes it's really boring, and it makes like it just makes sense. It's not some mystical magical thing. It's considering all of the characteristics we have to work with in order to make this model for like where people will live. Density estimation is like creating a heat map that shows population density across different neighborhoods. We're not interested in pinpointing any individual person, but rather in seeing which areas of the city have higher or lower densities of certain types of people. A Gaussian mixture model here would be like representing the city's density map as a blend of overlapping bell-shaped areas. Each bell shape or Gaussian represents a different kind of neighborhood with varying densities, from sparsely populated suburbs to dense urban centers. The model we create won't simplify or reduce the number of characteristics we're looking at. Instead, it will focus on capturing the full picture of the city's population density across all 5 characteristics. This density model will then tell us, for instance, that most people who fit a certain profile, for example, middle-income families with children, live in one area. So, for example, they need bigger houses, while other profiles fit better in different parts. So, like if they're a university student, they want to live near campus. It's like creating a detailed map that shows the hotspots where people with similar characteristics are likely to live within this 5-dimensional space. So right there, you can tell how that would be interesting. You can understand the markets if you're doing like real estate investing. So I do have a question here. What is the difference between a Gaussian bell shape and a parabola? Oh, they're really different. They're completely different. So a Gaussian bell shape, they're using different kinds of numbers. Okay, so in a really like basic way, is it to just say that they're representing different kinds of numbers? Like, is that enough to like in a nutshell say what the difference is? Yeah. Okay. So the Gaussian bell curve represents probabilities. It represents how data is spread around a mean, with values clustering in the center and tailing off towards the extremes. And a parabola represents a relationship in algebra, usually quadratic. It shows how one variable changes with the square of another. often in a physics or optimization context. Okay, thanks. That really helps. That's one of the things that makes mathematics so confusing is like you see this parabola shape and then you just like think like everything's a parabola, but like things can have like the exact same shape and look the exact same and be like completely different. Yeah, it can be tricky that way. So yeah, that's one thing to be careful about in mathematics. You see a graph, you really have to understand what is being shown on the graph, because the graph is going to look like any other graph you would see. So it's the details of the graph that really give it meaning. All right, so chapter 12 concludes the book with an in-depth discussion of the fourth pillar, classification. We will discuss classification in the context of support vector machines. Similar to regression, chapter 9, we have inputs x and corresponding labels y. However, unlike regression, where the labels were real valued, the labels in classification are integers, which require special care. So that's classification. Section 1.3 is exercises and feedback. We provide some exercises in part 1, which can be done mostly by pen and paper. So I do have a desk whiteboard here that I can use for that. Hopefully that'll be enough. I would really like to get a Saul Khan of Khan Academy uses a special drawing tool. I would like to get that, but I don't know where that comes from. I can look it up, and I don't want to. I'd rather just work with the tools I have than spend so much money all the time. So we provide some exercises in part 1, which can be mostly done by pen and paper or on a whiteboard, hopefully. For part 2, we provide programming tutorials, Jupyter notebooks, to explore some properties of the machine learning algorithms we discuss in this book. We appreciate that Cambridge University Press strongly supports our aim to democratize education and learning by making this book freely available for download here. Awesome. So I'm not even doing any sort of piracy or anything like that. This is a free book available for download at this link. So let's go to that link. You can look at it on GitHub. You can download it as a PDF. You can work with it direct in on this website, it looks like. And there's extra tutorials, so you can learn how to use Jupyter notebooks. Yeah, really good book. This is a great suggestion. And again, I learned of this from a Reddit comment I showed in one of my prior videos, where tutorials, errata, and additional materials can be found. Mistakes can be reported and feedback provided using the preceding URL. So that's one thing I do on this channel often. If I do find some errata, I do submit it. Much to the author's delight. People probably groan when they see my name. And if I'm perfectly honest, I think I already saw some errata. This is errata, right? This little tick signal on the bottom is errata. There shouldn't be a comma there. Like I think that's not there intentionally. Let's interact with ChatGPT. Okay, so you can see in the equation or in the mathematical statements, using mathematical symbols, that for some, a symbol that appears similar to a comma is shown prior to the exponent. Is this necessary to the mathematical statement, or does it appear to be errata? Yeah, but there's an extra. Yeah, but there's an extra comma, right? Like, is that comma supposed to be there? There's so in the exponent capital D sort of symbol, and then after the thing that looks like a capital R, but looks a bit different from that. There's what looks like a comma between the two. Like, what does that comma mean? Yeah. Oh, okay. It's part of the typograph. Okay, so the symbol is okay. Double line on the left side. What about on the right side of that? What about on the right side of that symbol? There appears to be a comma there. Yeah. Okay. So it's just a peculiarity of the font. Okay, so that's not necessarily errata. It's just a part of this symbol. But we can see that it's not always there. Like here it's, oh no, it is there. See, we can see that in very small detail. If I zoom in like 200%, and then we look at the statement. Oh, okay, I get it now. So I wasn't seeing a comma. If we zoom in 400%, what I was seeing was the curled foot of this symbol. So there isn't a comma anywhere here. It's just the way it was displayed on my screen. I couldn't see the curled foot correctly. I couldn't see that it was all a part of this character. So okay. All right. I'm happy with that. So now if I zoom back to 100%, now it looks like that comma returns, right? But it's just because of the pixels of my screen, and the font. It's like it's displaying that foot in a way that looks like it's disconnected from that symbol, but it's just like the curled up toes of that symbol. It's not its own symbol that is in addition to this symbol. It's a part of that symbol. All right, so let's try to see what let's try to get reminded of what that symbol is. So I need to make sure my bookmark is set. Yep, my bookmark's set at chapter 2. So let's go back to the highlights, and let's look at the fourth section of symbols on the next page, because I think it's there. Don't see it there. Okay, so let's try to find it somewhere. Here we go. So R raised to the n, it's an n-dimensional vector space of real numbers. And n-dimensional. And it's raised to the d, which is, it's raised to the number of dimensions indexed by d equals 1 throughout to d. Okay, cool. Bookmarks. And that's it for chapter 1. I think I'm gonna do an end here. Normally I can do an hour. Oh, and it's been an hour. So so that's it for this video. Stay tuned for the next part.